All right, 6.5, finding real roots of polynomials. So not talking about imaginary right now. We're focusing on the real roots. So let's get into it. So last section, 6.4, we use several methods for factoring polynomials. So remember, we can pull out GCFs. We can use a factor by grouping when there's 4 terms. We did the sum of cubes. We did the difference of cubes. So those were all several ways that we factored polynomials. And just like with quadratics, we can set a polynomial equal to 0, factor it, and use the zero product property to find its roots. So let's kind of do this first one. So on the first one, first thing I see is that I could pull out a greatest common factor of 3, and then the smallest x powers to the third. So I'm going to pull out a 3x to the third. Then I'm going to think about the distributive property and how I could get back to my expression up above. And so this would be 6x, and this would be 9. And now when I break this down, I'm going to have 3x to the third times, and I'm always going to want to try to keep going if I can. And I think if I factor that, it's actually x plus 3 squared, or x plus 3 times itself. So, looking at this number, I should have 5 zeros in here somewhere. And the zero product property says that one of these 3 chunks here have to be 0. If I multiply a bunch of things together and I get 0, somebody's got to be 0. So I get x equals -3, another x equals -3, and then, technically over here, this is really 3 times x times x times x, if I break it all the way down. So actually I have x equals 0 3 times. So that kind of accounts for all 5 of my roots. So 0, 0, 0, -3, -3. Let's move over to the next one. On this one here, I'm going to set it equal to 0 because it's not right now equal to 0. So let's set it equal to 0. And I get x to the 4th minus 13x squared plus 36 equals 0. And, this is a trinomial. So I'm going to just give it a shot. I can't really pull out a greatest common factor. But I'm going to see if I could just do it kind of the quadratic way. And I could get 2 numbers at the backside that have to multiply to make 36. They need to add to make the -13x squared. And my front terms need to multiply to make x to the 4th. So I think if I do x squared times x squared, that'll take care of the x to the 4th. If I combine them, I'm going to get an x squared term in the middle. And, I think that if I choose a -9 and a -4, that'll do it for me. Yeah, that's going to work out. So now I'm going to have -13x squared in the center, positive 36 at the end. But then both of these are difference of squares. These are difference of squares back from the quadratics chapter. So I can break each of these down. And, this one can be broken down as x plus 3 times x minus 3. That middle term will disappear. And then this one's going to be x plus 2, x minus 2. And so one of those parentheses has to equal 0. So it looks like I got -3, positive 3, -2, and 1. So all 4 zeros are there and they're all different. So notice on the one before, I had some repeats. This one, they were all distinct. They were all different. Remember, these are x-intercepts. They're telling me where my graph crosses the x-axis. All right, moving down, we have a little kind of a little fact here. I want to read about multiplicity. It says sometimes a polynomial has a factor that appears more than once. Notice in example 1, we had x equals -3 in 2 places. Then we had x equals 0 3 places. So it says the multiplicity, a vocab word here, of a root is the number of time it appears. So we would say that -3 would have a multiplicity of 2, and 0 would have a multiplicity of 5. Not 5, what am I saying? 3, for a total of 5. And then there's something else. There's a little graph here that kind of says when a real root has an even multiplicity. So when you have even, you happen 2 times or 4 times or 6 times, the graph touches the x-axis but does not cross it. So if you notice right here, that -3 had a multiplicity of 2. So this is the even situation. Notice that it just touches the graph. It doesn't cross the x-axis. It kind of comes up, just touches it, and it gets rejected and comes back down. So that's when you have an even multiplicity. Well, if we have an odd multiplicity, like 3, 5, 7, it's going to bend there. So it's going to come up, and then it's just going to bend. It doesn't get rejected, and then it keeps on going. So sometimes those are hard to tell. Like, is it just an intercept? Like, it just kind of crossed there? Or that little bend kind of tips me off that there might be a triple root going on, where over here there's a double root. So number 3 says identify the roots and state the multiplicity. So we're going to take a look at this on the graph, and I'm going to use Desmos to do this one. So I'm going to pull Desmos up, and actually I have it right here on the graph. So x to the third minus 9x squared plus 27x minus 27. You'll notice right here we have a bend. Now I'm not exactly sure. I'm pretty sure that that means that maybe it happened 3 times. All right, so I have x equals 3 times. But I'm going to steal this 1 0. I know there is a 0 there at 3. I'm going to steal that and show you how we can verify the other ones. So sometimes we can kind of cheat, and we can use the graph to get our first 0. And then after that, we can use synthetic division to get the rest. So let me show you what I mean. So from the graph, we are pretty sure that something is going on at x equals 3. So let's do synthetic division on that. So I'm going to use the 3, and I have 1, -9, 27, -27. And we're going to run this. So I bring the 1 down, then I multiply 3 times 1, and then add them up. 3 times -6, add them up, and 3 times 9, add them up. And I should get 0. If I don't get 0, then this was not true, but it is true. Well, what I can do now is I can use what's left. You know, since this was a power of 3, I know that this starts with x squared. And now I can use this to keep on factoring it, just like using quadratics. And I think 2 numbers times together to make +9, add to make -6. Well, that's an x minus 3 and an x minus 3. So I've just verified that all 3 of those, all 3 of these zeros are x equals 3. So, and that makes sense because we had odd multiplicity. So that tells me that there's going to be a bend at x equals 3. And that's what we saw when we clicked on Desmos. So sometimes you can use a graph to kind of tip you off, help you out a little bit. This is probably the most important part of this lesson, and it's called the rational root theorem. Some books also refer to this as the rational zero theorem. So those can kind of be used interchangeably. And basically what this does, why this is important, is it gives us possible, it gives us possible rational roots. Now remember, rational number is a number that either, it can be expressed as a fraction. So rational means it could be a decimal like 0.25. It can be a whole number. It could be a fraction like 1/3. It goes forever, but I know where it's going. Just remember that irrational numbers, this is just kind of review, irrational numbers would be like square root of 2, square root of 5, things that aren't perfect squares, or your numbers like pi that's another number that goes on forever. No pattern, no repeating, just numbers keep on coming out. Well, that's not what we're talking about here. We're talking about rational, the possible rational roots. And then we have this little chart here that basically says that if a polynomial has integer, positive or negative whole number coefficients, every rational root can be written in the form P over Q. So these are the rational ones, where P is a factor of the constant term. So P is a factor of the constant term, the term at the backside, and Q is a factor of the leading coefficient. So I'm going to slide down to get a little bit more room here, and this will make a little bit more sense to us. So what I'm going to do here is, when I'm focusing on P, this is the P, all right? And then when I'm focusing on Q, there's a 1 there. This is going to be a Q. Pretty much in this course, I'm always going to make Q be 1, and I'll kind of show you why. So to do P over Q, we need to list all the factors of P and all the factors of Q. We need to list them out. Well, factors of -6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are all the numbers that can go in there evenly. The Q part would just be plus or minus 1. So plus or minus 1. Now, these are nice because when 1's on the bottom, we're pretty much just locked in to these possibilities. If there was a 2 or a 3, you're going to end up with a lot of fractions. There's a lot of P over Q options. We might do one on the homework, but in the notes we're not really going to do one like that. So right now, I know that there are 8 possible rational roots. All right? There's 8 of them. And looking right here, I know that we have 3 zeros. So I'm going to hopefully be able to get 3 out of this group. Sometimes you can, sometimes you can't, but at least I have a starting point. So I need to try all those numbers, and what I'm going to do is I'm going to use synthetic substitution, but I'm going to show you how to make a table where you can try several of these kind of at once instead of having them all over your paper. So I'm going to kind of erase this to give myself a little bit more room. But here we go. So I'm remembering my choices. I'm going to write them over here to the side. So we need to test 1, 2, 3, and 6. We have 8 things to test. And what I'm going to do is I'm going to start off just like I normally would. But I'm going to put a column coming down. And I'm going to put columns across, rows across. And I could put 8 rows and try all 8 numbers, but here's where I'm going to try my numbers. Now, this is a synthetic substitution chart, and what we're going to do is we're going to leave out the number that we normally add. We're only going to write the answer down. So this takes a little bit of practice, but what I like to do is I usually try the positive numbers first. I could try +1, then -1, then +2, -2. So I might do it a couple different ways just to kind of show you. But let's try 1. So I'm going to try 1, and I'm going to plug it in, and I bring my 1 down. Well, then 1 times 1 is 1. Added to 2 will give me 3. 1 times 3 is 3. Added to -5, well, that's -2. And then 1 times -2 is -2. Added to -6. Well, that gives me a -8. So it looks like 1 is not a factor. All right? So this is not a factor because I didn't get 0 over here. So I know I can cross out the positive one. Maybe I try -1. Yeah, let's try -1. So I bring the 1 down. And -1 times 1 is -1. Added to 2 gives me 1. -1 times -1 is -1. Added to the -5 gives me -6. Negative 1 times negative 6 is 6. Added to the negative 6, hey, sweet. This one is a factor. We got what we wanted. So we know that x equals negative 1 is one of our zeros. Now, I could just keep on trying all the numbers on the list. I could go to the 2s, the 3s, the 6s. But a lot of times, once you get that first one, you could then use that row because it's going to be a quadratic now. Notice because this was x to the third, this is just x squared plus x minus 6 equals 0. And I think I can just factor now. And it might be a little quicker to get my other two zeros. So I need to come up with two numbers that multiply to make negative 6, but add to make positive 1. So I think if I choose these right, I think that multiplies to make negative 6, adds together to make 1. So those are my factors. So I know I have a 0 at negative 3 and a 0 at 2. So here are my three zeros. So I kind of stopped doing the synthetic division, and I just chose the factor because I thought it was quicker. I kind of got 2 for 1 there. But you could just keep right on going down the list and try those. Now occasionally, you get this thing right here, you finally get a factor to be 0, and then you bring down the next line, and it's not factorable. So that might be a situation where you have two complex numbers because you're going to do the quadratic formula, and you could end up having some irrational answers there that are not from this list up above. This list only gives us the rational ones. So if you have something that you do the quadratic formula and you end up with a radical in your answer, it's not going to be from this list. So it's a little bit limited. And I'll be honest, most of the time nowadays we have technology. We're not going to really go through this, but I need to kind of teach you so you appreciate the technology. So let's try number 5. So let's list out the possible zeros, possible rational zeros, I should say. So I'm going to do my P over Q, which is going to be, P is negative 20. So I think we got plus or minus 1, 2 goes in there, 4 goes in there, 5 goes in there, 10 goes in there, and 20 goes in there. Q is just going to be plus or minus 1. I don't know why I put the number symbol there, but got a little bit confused. Plus or minus 1. So basically, again, like I said, what's normally going to happen in our class is we're just going to look at these because there's a 1 on the bottom. Just makes life a little bit easier. So when I look at this, I have 6 plus the negatives. I have 12. Right now there's 12 possible rational zeros. All right, we got 12 of them. So I'm just going to kind of start my table. And I have 1, I have 8, I have 11, I have negative 20. And we'll try the first row. I'll try 1. So here's where I try these things up here. So I try 1. So you slide the 1 down. 1 times 1 is 1. Added to 8 gives me 9. 1 times 9 is 9. Added to 11 gives me 20. 1 times 20 is 20. Added to negative 20 gives me 0. So I got lucky. Well, this is really lucky. The very first one worked. So I know that x equals 1 is one of the zeros. So I got 1 0. Well, now what I'm going to do is I'm going to try to use what's left to factor it and see if I get lucky here. X squared plus 9x plus 20. Hey, I think we can do that. 4 and 5 would be a combination. So being able to factor a quadratic is really, really useful for this type of stuff. So I have another 0. I get negative 4, and I get negative 5. So there's 1, and boom. we got them. And it saved me a lot of time because I might have tried in my chart 1, 2, 4, 5, 10, 20. Then to go through the negatives, it would have been a while before I would have got back. It would have been like my 9th and 10th row of that chart. So once you crack one, try to factor that quadratic and get your other two. It's just going to make life a little bit easier. All right, let's go down to the next one. I don't really know why that line just showed up across there, but this line somehow the copier just kind of put it there. So I don't really know what that's for, but just ignore it. So on this one, when I do my P over Q, I got positive 6. So that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. The bottom, plus or minus 1. So I need to test these. So I have 8 things I need to test. So when I do my first row, maybe I'll just use this line. I got to put a 0 in the x squared position because there was no x squared term. So don't lose that 0, otherwise things are going to get kind of screwed up. And so I'm going to bring my table down. Got to try some things here. So this is kind of my try column. And I don't know, let's try one. It's been lucky for us before. So I try 1, bring my 1 down. 1 times 1 is 1, added to 0 is 1. 1 times 1 is 1, added to negative 11, it's negative 10. 1 times negative 10 is negative 10 added to 6, negative 4. So I know that 1 doesn't work. All right, so the positive 1 is gone. So I could either try negative 1 or I could try 2. I don't know, I'm just going to go to 2. Slide the 1 down, 2 times 1 is 2, added to 0. 2 times 2 is 4, added to negative 11, that's negative 7. 2 times negative 7 is negative 14, added to 6, that's negative 8. Well, that didn't work. So positive 2 is gone. Let's try 3. Bring the 1 down from the top. So remember, these, you can kind of just cross all these out because they might just kind of mess you up if they're not working. But use the top row. So slide the 1 down. 3 times 1 is 3. Added to 0 is 3. 3 times 3 is 9. Added to negative 11. That's negative 2. 3 times negative 2 is negative 6. Added to 6. Boom. So I got my 0. So I know that x equals 3 is one of the answers. And now I'm going to try to use this one. Let's see if I can make it work. And trying to make negative 2, the only way to make negative 2 is positive 1 and negative 2, or negative 1 and positive 2. Neither of those add up to 3. So kind of in a bit of a pickle. And I could go through and I could test everybody else, but right now I'm thinking that there's only going to be one rational root. All right, because what's probably going to happen is I'm going to have to use the quadratic formula on this one. So let me use the quadratic formula. So I have my x equals 0 as my one rational root. But then I got negative b plus or minus b squared minus 4 times a times c all over 2a. Yeah, and I'm going to have negative 3 plus or minus the square root of, well, that's 9 plus 8, which is 17, divided by 2. And that's going to be irrational. That square root of 17 is going to be a nasty decimal that goes on forever. So my other two zeros, we don't really need them because it said find the rational zeros. But my other two zeros would be negative 3 plus the square root of 17 over 2 and negative 3 minus the square root of 17 over 2, which are both going to be decimals. I could crank that out if I wanted to, if I could find a calculator here. So negative 3 plus the square root of 17 divided by 2 is 0.56. 155, 2, 8, blah, 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 blah. Just keeps on going. The other one's going to be negative 3. Take away the square root of 17 divided by 2, which is negative 3.56, 155, 2, 8, blah, 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 blah. It just keeps on going. So roughly at a half, negative 3.5, and then we got the 1 at 3. So if we were to put this into Desmos, we should see those places as crossing points. Let's try it. X to the third minus 11x plus 6. So x to the third minus 11x plus 6. And sure enough, we have the 3. Then we have the 1 at 0.56, blah, 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 blah. And we have that 1 at negative 3.56, blah, 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 blah. So this one didn't give me 3 nice rational ones. It only gave me 1. So I just wanted to kind of show you that that list is only the possibilities. It doesn't really tell you that it has to be from that list. All right, last one, marketing design. So it says a popcorn producer, clear out this old stuff. Popcorn producer designed a new box. The width is 2 inches less than the length. So this must be the width. This is the length. And then the height is 5 more than the length. And the volume must be 24. V is 24. So remember, volume is length times width times height. And so the volume is x times x plus 5 times x minus 2. I think I wrote those two backwards. It's height and width, but it doesn't matter. I got to multiply them all 3 anyway. So I'll do the first 2. So that was just that piece. Now we got to go and we got to do this last part. So I'm going to have 24 equals, that'll be x to the third minus 2x squared plus a 5x squared minus 10, which is, and I want to set this equal to 0 also. So I have x to the third plus 3x squared. And then I need to, oh, this was a minus 10x. The minus 10x. And then I got the negative 24, because I got to move that 24 over. So here's basically, this is where what we did our last few problems. So this is kind of my starting point. And, oh, this kind of sucks, because when you do your P over Q, we know that Q is just positive or negative 1, but 24 has got a bunch of factors. We got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Oh, I missed 8. 8 goes in there. So maybe I'll do the 8 here. Plus or minus 12. And then finally plus or minus 24. So 1, 2, 3, 4, 5, 6, 7, 8 times 2. There's 16 possible zeros. But luckily when I look at this question, x cannot be negative, because if x is negative, we won't have a length. So we can eliminate, so I'm going to say minus all the negatives. So now I'm down to 8. All right, so we can kind of go in here and we can say, well, we don't have to test any of these negative ones, because then we wouldn't have a problem. And I think if I plug 1 in or 2 in, my width is going to be an issue. Like, in order for this to be positive, x has to be bigger than 2. So that kind of wipes out these guys. So actually, it looks like we got it down to 6. So we have it down to 6 possibilities. So I'm going to use these coefficients here, 1, 3, negative 10, negative 24. So 1, 3, negative 10, negative 24. So 1, 3, negative 10, negative 24. And we're going to start testing some things. See if we can crack this thing open. So let's try 3. Bring the 1 down. 3 times 3 is 3. Added 3 is 6. 3 times 6 is 18. 18 added to negative 10 is 8. 3 times 8 is 24. Added negative 24. Booyah. Got lucky. So I know that x equals 3 could be an option. And then I can use this quadratic right here, x squared plus 6x plus 8, to try to factor it. Let's see if we can factor this thing. 2 and 4. X plus 2, x plus 4. And both of those give me negatives, which we already determined x cannot be negative or this problem doesn't exist. So it looks like the correct answer here has got to be 3. And if I test it out, this is going to be 3 times 1 times 8. And 3 by 1 by 8 will give me 24. So we've answered the question. All right, hopefully you got some practice at using the rational root theorem, creating a synthetic division table for a shortcut to help us find some of those rational zeros. See you.